As we saw in Chapter 2, the first quantitative information about atomic masses came from the work of Dalton, Gay-Lussac, Lavoisier, Avogadro, and Berzelius. By observing the proportions in which elements combine to form various compounds, 19th century chemists calculated relative atomic masses. The modern system of atomic masses, instituted in 1961, is based on carbon-12 as the standard in the system. Carbon-12 is assigned a mass of exactly 12 atomic mass units, and the masses of all other atoms are given relative to this standard. The most accurate method currently available for comparing the masses of atoms involves the use of the mass spectrometer. In this instrument, diagrammed in Figure 3.1, atoms or molecules are passed into a beam of high-speed electrons, which knock electrons off the atoms or molecules being analyzed and change them into positive ions. Accelerating ion produces its own magnetic field. Interaction with the applied magnetic field occurs, which tends to change the path of the ion. The amount of path deflection, for each ion depends on its mass. The more massive ions are deflected, the smallest amount, which causes the ions to separate, as shown in Figure 3.1. A comparison of the positions when the ions hit the detector plate gives very accurate values of the relative masses. For example, when carbon-12 and carbon-13 are analyzed in a mass spectrometer, the ratio of their masses can be found to be 1.0836. Since the atomic mass unit is defined such that the mass of carbon-12 is exactly 12 atomic units, then on the same scale, mass of carbon-13 is 13.003355 units. The masses of other atoms can be determined in a similar fashion. The mass for each element is given on the table on the front cover of this text. This value, even though it is actually a mass, is sometimes called the atomic weight for each element. Look at the value of the atomic mass of carbon-12 given in the table. You might expect to see 12, since we said the system of atomic masses is based on carbon-12. However, the number given for carbon is not 12, but 12.01. Why? The reason for this apparent discrepancy is that the carbon found on Earth is a mixture of the isotopes carbon-12, carbon-13, and carbon-14. All three isotopes have 6 protons, but they have 6, 7, and 8 neutrons, respectively. Given natural carbon is a mixture of isotopes, the atomic mass we use for carbon is an average value reflecting the average of the isotopes composing it. The average atomic mass for carbon is computed as follows. It is known that natural carbon is composed of 98.89% C12 atoms and 1.11% carbon-13 atoms. The amount of carbon-14 is negligibly small at this level of precision. Using the masses of carbon-12 and carbon-13, we can calculate the average atomic mass for natural carbon as follows. In this text, we will call the average mass for an element the average atomic mass, or simply the atomic mass for that element. Even though natural carbon does not contain a single atom with mass 12.01, for stoichiometric purposes, we can consider carbon to be composed of only one type of atom with a mass of 12.01. This enables us to count atoms of natural carbon by weight of a sample of carbon. Recall from section 3.1 that counting by weighing works if you know the average mass of the units being counted. Counting by weighing works just the same for atoms as for jelly beans. For natural carbon with an average mass of 12.01, atomic mass units to obtain 1,000 atoms would require weighing out 12.01 atomic mass units, 12,010 atomic mass units for natural carbon. As in the case of carbon, the mass for each element listed on the table inside the front cover of the text is an average value based on the isotopic composition of the naturally occurring element. For instance, the mass listed for hydrogen is the average mass for natural hydrogen, which is the mixture of H1 and H2. No atom of hydrogen actually has the mass 1.008. In addition to being useful for determining accurate mass values for the individual atoms, the mass spectrometer is used to determine the isometric composition of a natural element. For example, when a sample of natural neon is injected into a mass spectrometer, the mass spectrometer, shown in figure 3.2, is obtained. The mass spectrum is obtained. The areas of the peaks or the heights of the bar indicate the relative abundance of neon 10, or neon 20, and neon 21, and neon 22 atoms.